I'm so glad you could make it tonight. You found Science Blanket, your quiet space for wonder. Have you ever looked at a distant peak and felt like you were looking at a slow-motion dream? Tonight, we're wrapping ourselves in the science of the Earth, specifically the silent, majestic life of mountains. We often think of them as solid, unmoving objects, but they are actually ghosts of the crust, trillions of tons of stone and minerals suspended in a delicate balance between the deep mantle and the void. From the high, jagged summits that look like frozen waves to the heavy, snow-covered blankets that bring the silence, mountains are the visible signature of the Earth's invisible movement. As we begin, imagine yourself resting on a high, silent peak, feeling as steady and grounded as the stone itself. You don't need to understand the physics of tectonic plates or the names of the altitudes tonight. Just let the slow, ancient weight of the mountain tuck you in. If this blanket of stone helps you find rest, I'd love for you to subscribe and join our community of sleepy explorers. Now, take a slow, deep breath. Feel your lungs expand and then empty, as steady as a mountain breeze. Let the weight of your day settle into the dark earth. Relax your jaw, let your shoulders drop, and sink into the softness of your bed. Let's explore the quiet wonders of the mountains together. The story of how mountains come to tower over our planet is one written across millions upon millions of years, a narrative of immense forces working beneath our feet and shaping the very face of the Earth itself. When you gaze up at a mountain peak piercing the clouds, you're looking at the result of processes so gradual and yet so powerful that they bend solid rock as though it were clay. Mountains form through three primary mechanisms, each remarkable in its own right. Tectonic forces, those tremendous movements of the Earth's crustal plates, create some of the most dramatic peaks. Volcanic activity builds mountains through the accumulation of molten rock and ash. And erosion, that patient sculptor, carves away at existing landforms to reveal mountains that were hidden within. The timescales involved are almost impossible for us to truly comprehend, stretching back through geological epochs that dwarf all of human history. Among the mountains born from tectonic forces, fold mountains represent perhaps the most dramatic expression of the Earth's raw power. Picture two massive sections of the planet's crust, floating on the semi-molten mantle below, slowly drifting toward one another over millions of years. When these tectonic plates finally collide, something has to give. The rock layers between them buckle and fold, crumpling upward like a rug pushed across a floor. The compression is so intense that solid rock bends into waves, creating the folded structures that give these mountains their name. The Appalachian Mountains in North America and the Alps of Europe are classic examples of fold mountains, their layered rock strata telling the story of ancient collisions that occurred hundreds of millions of years ago. You can sometimes see these folds exposed in cliff faces and road cuts, the layers of rock bent into S-curves and U-shapes, a permanent record of unimaginable forces. But not all mountains form through folding and compression. Block mountains, also known as fault block mountains, arise through a different mechanism entirely. Deep beneath the surface, the Earth's crust is constantly under tension and pressure, causing it to fracture along lines of weakness called faults. Sometimes these faults don't just crack the rock, they cause entire sections of the crust to shift vertically relative to one another. Imagine a series of enormous blocks of rock, some being pushed upward while others drop downward along these fault lines. The blocks that rise become mountains, while those that fall create valleys. The Sierra Nevada range in California is a spectacular example of fault block mountains, where a massive section of crust tilted upward along its eastern edge, creating the dramatic escarpment that rises so abruptly from the Nevada desert. These mountains often have one steep face where the fault line is exposed and a more gradual slope on the opposite side. Dome mountains represent yet another fascinating way that mountains can form, and their origin is hidden entirely beneath the surface until erosion reveals their structure. Deep within the earth, magma rises from the mantle, seeking pathways to the surface. Sometimes this molten rock doesn't quite make it all the way up. Instead, it collects beneath layers of existing rock, forming massive underground chambers. As more magma accumulates, it pushes upward with tremendous force, bowing the overlying rock layers into a dome shape. The magma eventually cools and solidifies beneath the surface, creating a hard igneous core, while the rock layers above remain arched over it like a blister. Over time, erosion wears away the softer overlying layers, eventually exposing the hardened magma core at the center. The Black Hills of South Dakota are a beautiful example of dome mountains, their rounded shape reflecting the way they were pushed upward from below. Volcanic mountains, on the other hand, are built from the outside in rather than being pushed up from below. These are the mountains most of us picture when we think of volcanoes, the classic cone-shaped peaks like Mount Fuji in Japan or Mount Rainier in Washington state. They form through a process of accumulation, built up layer by layer through countless eruptions over thousands or even millions of years. Each eruption adds a new layer of lava, ash, and other volcanic materials to the growing structure. The lava flows down the slopes and solidifies, the ash settles and compacts, and slowly, incrementally, the mountain grows taller and wider. Some volcanic mountains are surprisingly young in geological terms. The island of Surtsey, off the coast of Iceland, literally emerged from the ocean between 1963 and 1967, a brand new volcanic mountain born in just 4 years. Yet other volcanic mountains, like the massive shield volcanoes of Hawaii, have been building for millions of years, their gentle slopes hiding an enormous mass of accumulated lava. There's something almost poetic about residual mountains, which emerge not through any dramatic uplift or volcanic drama, but through the quiet persistence of erosion. These mountains were hidden all along, waiting to be revealed. Imagine a landscape where different types of rock exist side by side, some hard and resistant to weathering, others soft and easily worn away. Over millions of years, wind, water, ice, and chemical weathering attack all the rock equally, but the softer materials erode much faster. Gradually, the landscape lowers as the soft rock is carried away, but the hard rock remains standing, eventually emerging as mountains simply because everything around them has been removed. It's as though a sculptor were chiseling away everything that isn't a mountain, leaving the mountain behind. The Catskill Mountains in New York are examples of residual mountains, high plateaus where resistant rock types have outlasted the erosion that carved away the surrounding terrain. What's truly remarkable is that mountains aren't just surface features perched atop the Earth's crust. Every mountain has roots, extensions that reach deep down into the layers beneath. This might seem counterintuitive at first. Why would something tall need deep foundations? The answer lies in a principle called isostatic balance. The Earth's crust essentially floats on the denser, semi-molten mantle below, much like icebergs float in water. And just as most of an iceberg's mass is hidden beneath the surface, mountains too have a hidden bulk extending downward. The taller the mountain, the deeper its roots must reach to maintain balance. These roots can extend dozens of kilometers down into the mantle, ensuring that the mountain doesn't simply sink under its own weight. It's a delicate equilibrium, a constant balancing act between the mass of the mountain above and the buoyancy provided by the mantle below. Mountains are not static monuments, frozen in time. They exist in a constant state of flux, engaged in an eternal battle between the forces that build them up and the forces that tear them down. Young mountains, those formed relatively recently in geological terms, continue to rise as the tectonic forces that created them remain active. Meanwhile, these same young mountains are immediately attacked by erosion, weathering, and mass wasting processes that begin sculpting and lowering them from the moment they emerge. Older mountain ranges, where the tectonic forces have long since ceased, gradually succumb to erosion's patient work, becoming lower and more rounded with each passing millennium. The ancient Appalachian Mountains, once as tall as the Himalayas, have been worn down over hundreds of millions of years into the gentler, more weathered forms we see today. Yet they still stand, a testament to the hardness of their rock and the immensity of time required to level even these ancient giants. The Himalayas represent youth in mountain terms, though their formation began around 50 million years ago when the Indian subcontinent collided with Asia. In the grand scheme of Earth's 4.5 billion year history, 50 million years is remarkably recent, and the Himalayas show it in their dramatic, jagged peaks and their extraordinary height. Mount Everest, the highest point on Earth's surface at over 8,800 meters, is part of this youngest and tallest mountain range on the planet. The forces that created the Himalayas are still at work today, making them what geologists call tectonically active mountains. And here's something almost magical to contemplate as you drift towards sleep. The Himalayas are still growing, still rising toward the sky at this very moment. The Indian plate continues to push northward into the Eurasian plate, and though the movement is imperceptibly slow from our human perspective, it's measurable. Scientists estimate that the Himalayas are rising by several millimeters each year, roughly the rate at which your fingernails grow. In a single human lifetime, these mountains might rise by 1/3 of a meter or more. It's a reminder that the earth beneath us is never truly still, that the mountains we think of as eternal symbols of permanence are themselves temporary features, rising and falling in the planet's endless dance of creation and destruction, though on a timescale so vast it transforms them into something that seems, to us, like forever. When we think about mountains, we often picture specific peaks or ranges, those dramatic landmarks we've seen in photographs or visited ourselves. But if you could step back far enough to see the entire planet at once, you'd realize that mountains are not rare exceptions dotting an otherwise flat world. They are, in fact, one of the Earth's dominant landscape features, covering an astonishing portion of our planet's surface. Roughly 1/4 of all the land on Earth is mountainous terrain. Think about that for a moment. Between 22 and 27% of every continent, every landmass, is shaped by these towering geological formations. The exact percentage varies depending on how you define what counts as a mountain, whether you include foothills and high plateaus, or limit the definition to only the tallest and most dramatic peaks. But by any measure, mountains are everywhere, shaping climates, dividing ecosystems, influencing where people live and how civilizations develop. From the frozen peaks of Antarctica to the tropical highlands of Africa, from the ancient worn-down ranges of Australia to the still-rising giants of Asia, mountains define the character of our planet's land surfaces in ways both obvious and subtle. Among all the mountain ranges that rise above the land, one stands out for its sheer length and grandeur. The Andes form the longest continental mountain range on Earth, a spine of stone that runs like a backbone along the entire western edge of South America. If you were to walk the length of the Andes, you would travel more than 4,300 miles, passing through 7 different countries along the way. Your journey would begin in Venezuela in the north, where the Andes emerge from the Caribbean coastal ranges, and would carry you southward through Colombia, where the range splits into 3 distinct cordilleras, parallel chains of mountains separated by deep valleys. You'd continue through Ecuador, where the Andes are punctuated by some of the world's highest active volcanoes, their snow-capped peaks rising almost directly from the equator. In Peru and Bolivia, you'd cross the Altiplano, that vast high-altitude plateau nestled between the eastern and western ranges, a cold, windswept land where indigenous peoples have thrived for thousands of years despite the thin air and harsh conditions. Further south through Chile and Argentina, the Andes would reveal yet more faces, from the wine country valleys to the glaciated peaks of Patagonia, before finally dwindling into the islands and channels at the southern tip of the continent. Throughout this entire journey, you'd never drop below mountainous terrain, never escape the influence of this magnificent range that has shaped South American geography, climate, and culture so profoundly. But as impressive as the Andes are, they are not actually the longest mountain range on Earth. That distinction belongs to a range that most people never see and many never even think about because it lies hidden beneath the ocean waves. The mid-ocean ridge is a mountain range so vast it makes all terrestrial ranges seem modest by comparison. This submarine mountain system extends more than 65,000 kilometers around the planet, snaking through the Atlantic, Indian, Pacific, and Arctic oceans like the seam on a baseball. If you could drain the oceans away, you'd see a continuous chain of underwater mountains, volcanic peaks, and deep rift valleys forming the most extensive mountain range on Earth. The mid-ocean ridge marks the boundaries where tectonic plates are pulling apart, where new oceanic crust is constantly being born from upwelling magma. As the plates separate, molten rock rises from the mantle to fill the gap, creating new seafloor and building these submarine mountains in the process. In a few places, the ridge actually breaks the ocean surface, creating volcanic islands like Iceland, which sits directly atop the mid-Atlantic ridge. There, you can stand with 1 foot on the North American plate and 1 on the Eurasian plate, literally straddling the gap between continents. But for most of its enormous length, the mid-ocean ridge remains kilometers beneath the waves, explored only by deep-sea submersibles and sonar mapping, a hidden mountain range vaster than anything on land. Back on the continents, some mountain ranges are notable not just for their length but for their concentration of extreme peaks. The Karakoram Range, located where Pakistan, India, and China meet, hosts some of the densest clusters of high peaks anywhere on Earth. This relatively compact range contains 4 mountains over 8,000 meters in elevation, including K2, the second highest mountain in the world. But it's not just the very tallest peaks that make the Karakoram remarkable. The range is packed with mountains over 7,000 meters, a concentration of extreme altitude found nowhere else. The name Karakoram means black gravel in the local languages, referring to the dark rock and steep, jagged appearance of these mountains. Unlike the somewhat more accessible Himalayas to the southeast, the Karakoram is remote and forbidding, with some of the most challenging climbing conditions anywhere. The range also contains some of the longest glacier outside the polar regions, rivers of ice that flow down between the peaks, grinding away at the rock and carving the landscape into ever more dramatic forms. It's a landscape of superlatives, where altitude and ruggedness combine to create some of the most extreme mountain terrain on the planet. Mountains are not limited to the more temperate and tropical regions of Earth. They exist even in the most inhospitable places, including the frozen continent of Antarctica. The Transantarctic Mountains form one of the longest mountain ranges on the continent, stretching more than 3,500 kilometers across Antarctica and effectively dividing the continent into two distinct regions, East Antarctica and West Antarctica. These mountains rise dramatically from the edge of the ice sheet, their exposed peaks and ridges creating a stark contrast with the endless white ice that surrounds them. The Transantarctic Mountains are incredibly ancient, with some rocks dating back more than 3 billion years, making them among the oldest mountain rocks on Earth. Yet despite their age, these mountains still rise to impressive heights, with some peaks exceeding 4,500 meters. The range creates a significant barrier to ice flow, channeling glacier through specific passes and valleys as the ice sheet slowly moves toward the ocean. In summer, the exposed rock becomes one of the few ice-free areas in Antarctica, a landscape so barren and cold that scientists use it as an analogue for Martian conditions, testing equipment and protocols for future missions to the Red Planet. But not all of Antarctica's mountains are visible above the ice. Hidden beneath the vast East Antarctic ice sheet lies one of the continent's most mysterious features, the Gamburtsev Mountains. These peaks were only discovered in the 1950s through seismic surveys that could see through the ice, and they remain one of the least understood mountain ranges on Earth simply because they're completely buried under ice that's up to 4 kilometers thick. What scientists have discovered is remarkable. The Gamburtsev Mountains rival the Alps in size and elevation, with peaks rising to nearly 3,000 meters above the surrounding terrain, or they would if they weren't covered by ice. The range spans about 1,200 kilometers, roughly the size of the European Alps, creating dramatic topography that's completely hidden from view. What makes these mountains particularly puzzling is their age and condition. They're ancient mountains, possibly 1 billion years old or more, yet seismic imaging suggests they have the sharp, jagged peaks characteristic of young mountains. By all rights, such old mountains should have been worn down by erosion long ago. The fact that they retain such dramatic relief while buried under ice has led scientists to propose various theories about how they've been preserved, including the possibility that the ice sheet itself has protected them from erosion, or that they've been uplifted repeatedly over time. The Gamburtsev Mountains remain one of Earth's most enigmatic features, a ghost range hidden in the white heart of Antarctica. When we shift our view back to the oceans, we find yet more hidden mountains beyond the mid-ocean ridge. Scattered across the ocean floor are thousands upon thousands of seamounts, underwater mountains that rise from the abyssal plains but don't quite reach the surface. To qualify as a seamount, a submarine mountain must rise at least 1,000 meters from the surrounding seafloor, and by that definition, scientists have identified tens of thousands of these features, with estimates suggesting there may be more than 100,000 seamounts in total across all the world's oceans. Most seamounts are extinct volcanoes, formed over hot spots in the mantle where magma punches through the oceanic crust, building volcanic mountains that eventually go dormant as the tectonic plate carries them away from the heat source. Some seamounts rise just a few hundred meters below the surface, shallow enough that waves break over them even in calm seas, creating shipping hazards. Others are truly deep features, their summits still thousands of meters below the ocean surface. What makes seamounts particularly important is their role as oases of life in the deep ocean. The slopes of these underwater mountains create different current patterns and upwellings that bring nutrients from the deep, supporting diverse communities of marine life. Many seamounts are covered in deep-sea corals and serve as habitat for fish, sharks, and other creatures. They're biological hotspots in the otherwise relatively barren abyssal plains, underwater mountains that shape not just the geology of the ocean floor but its ecology as well, creating islands of life in the deep sea. There's something about the idea of the highest mountain that captures human imagination in a way few other geographical features can. We want to know which peak stands tallest, which summit reaches closest to space, which mountain represents the ultimate challenge. And when people ask about the highest mountain on Earth, the answer that comes back is almost always the same: Mount Everest. This legendary peak, known as Sagarmatha in Nepali and Chomolungma in Tibetan, rises to an officially measured height of 8,848 meters above sea level. That measurement, agreed upon by Nepal and China in 2020 after a joint survey, represents the height of the rock summit plus the snow and ice cap that crowns it. To put that elevation in perspective, commercial aircraft typically cruise at altitudes between 10 and 12,000 meters, meaning Everest's summit juts more than 3/4 of the way to typical cruising altitude. The air at the top contains only about 1/3 the oxygen found at sea level, thin enough that climbers must usually breathe supplemental oxygen to survive. The mountain straddles the border between Nepal and Tibet, its summit technically touching both, and it has become the ultimate destination for mountaineers, the defining achievement in high-altitude climbing despite the terrible dangers and the growing crowds that now gather on its slopes during the brief climbing seasons each year. What makes Everest's status as the world's highest mountain even more remarkable is that it hasn't finished growing yet. The mountain continues to rise slightly, pushed upward by the same tectonic forces that created the entire Himalayan range millions of years ago. The Indian tectonic plate is still pushing northward into the Eurasian plate, and that ongoing collision keeps squeezing the rock upward. Scientists estimate Everest gains approximately 4 millimeters in height each year, though the exact rate varies and is difficult to measure precisely. 4 millimeters might not sound like much, barely thicker than a few sheets of paper, but over geological time, this steady accumulation adds up. In 1,000 years, Everest could be 4 meters taller than it is today, assuming nothing else changes. Of course, other things do change, which makes the mountain's future height impossible to predict with certainty. But for now, Everest continues its slow, inexorable rise, pushed upward by forces operating deep beneath the surface, forces that have been at work for 50 million years and show no signs of stopping. Yet even as tectonic forces push Everest higher, other forces work to tear it down. Erosion is the eternal enemy of mountains, and at Everest's extreme altitude, erosion takes many forms. Wind scours the exposed rock and ice, carrying away tiny particles with each gust. The freeze-thaw cycle, where water seeps into cracks, freezes, expands, and breaks the rock apart, operates constantly in this environment. Avalanches strip enormous amounts of material from the mountain slopes, sending thousands of tons of snow, ice, and rock tumbling down to lower elevations. Glaciers grind away at the mountain's flanks, slowly carving valleys deeper and carrying away the debris. All of this erosion offsets some of the tectonic growth, meaning the mountain's net change in height is less than the uplift alone would suggest. In fact, scientists believe that erosion removes material from Everest at roughly 2 millimeters per year, about half the rate of tectonic uplift. This creates a dynamic equilibrium where the mountain continues to grow, but more slowly than the tectonic forces alone would produce. It's a constant battle between creation and destruction, between the forces building the mountain up and those tearing it down, and this battle will continue for millions of years to come, long after human civilization has perhaps faded into geological history. Now here's where things get interesting, because whether Everest is truly the tallest mountain on Earth depends entirely on how you define tallest. If you measure from base to summit, from the bottom of the mountain to its peak, a different mountain claims the record. Mauna Kea, a dormant volcano on the Big Island of Hawaii, rises an astounding 10,000 meters or more from its base on the ocean floor to its summit. Only about 4,000 meters of that height is actually visible above sea level. The rest is hidden beneath the Pacific Ocean, but the mountain itself is a continuous structure rising from the seafloor. If you could drain the Pacific and see Mauna Kea in its entirety, you'd be looking at the tallest mountain on Earth, dwarfing Everest by more than a kilometer. Mauna Kea is one of 5 volcanoes that together form the Big Island of Hawaii, and like the others, it was created by a volcanic hotspot, a plume of magma rising from deep in the Earth's mantle. As the Pacific Plate slowly moves northwest over this hotspot, the volcano gradually drifted away from its magma source and went dormant, though other volcanoes on the island remain active. The summit of Mauna Kea is high enough and far enough from coastal moisture that it's one of the best places on Earth for astronomical observation, and its peak is crowned with some of the world's most powerful telescopes, instruments that peer into the depths of space from atop Earth's tallest mountain, at least by one measure. If we return to land-based measurements but change what we're measuring, we find yet another claimant to the title of tallest. Denali, the highest peak in North America, has the greatest vertical rise on land of any mountain on Earth when measured from its base to its peak. Denali rises approximately 6,000 meters from its base to its summit elevation of 6,190 meters above sea level. What makes this vertical rise so impressive is that Denali sits on a relatively low base, unlike many other tall mountains that rise from already elevated plateaus. The Himalayas, for instance, rise from the Tibetan Plateau, which itself sits at elevations of 4,000 to 5,000 meters. So while Everest is taller in absolute elevation, its vertical rise from its immediate base is less dramatic than Denali's sheer ascent from the lowlands of Alaska. When you approach Denali from the north, it dominates the horizon in a way few mountains can, its massive bulk rising in an almost unbroken sweep from the surrounding terrain. The mountain was called Mount McKinley for many years, but in 2015 it officially reverted to its traditional Alaska native name, Denali, which means the High One or the Great One in the Koyukon language, a fitting name for a mountain that stands so dramatically above everything around it. Each continent has its own highest peak, its own superlative summit, and Europe's highest mountain is Mount Elbrus, located in the Caucasus Mountains of Russia, right on the border between Europe and Asia. The question of whether Elbrus is truly in Europe depends somewhat on where you draw the boundary between Europe and Asia, a question that has been debated for centuries. The most common convention places the boundary along the main ridge of the Caucasus Mountains, and by that definition, Elbrus, which sits on the northern side of the range, falls within Europe. At 5,642 meters, Elbrus is a dormant volcano with 2 summits, the western summit being slightly higher than the eastern one. The mountain is heavily glaciated, its slopes covered in ice that feeds rivers flowing north and south from the peak. Elbrus has become a popular destination for mountaineers seeking to climb the highest peaks on each continent, part of the so-called 7 Summits Challenge. While not technically as difficult as some other major peaks, Elbrus demands respect for its severe weather, extreme cold, and the altitude-related challenges that come with any mountain above 5,000 meters. In South America, where the Andes form that spectacular spine running the length of the continent, the highest peak is Aconcagua, which holds not just 1 but 2 superlatives. It is both the highest mountain in the southern hemisphere and the highest mountain in the western hemisphere, reaching an elevation of 6,961 meters. Located in Argentina, near the Chilean border, Aconcagua sits at the northern end of the southern Andes, in a region where the mountains reach their greatest heights. The mountain is not volcanic but rather was uplifted by the subduction of the Nazca Plate beneath the South American Plate, the same tectonic process that created the entire Andes range. Aconcagua's normal climbing route is considered one of the easier paths up any of the world's highest peaks, not requiring technical rock or ice climbing skills, but the mountain should not be underestimated. The extreme altitude, unpredictable weather, and fierce winds that can exceed 200 kilometers per hour have claimed many lives. The mountain's name may come from a phrase in the indigenous Quechua language meaning stone sentinel, or possibly from Mapuche words meaning on the other side of the Aconcagua River, but like many ancient place names, its exact etymology has been lost to time. Africa's highest mountain, Mount Kilimanjaro, holds its own special distinction. Rising 5,895 meters above sea level in Tanzania, Kilimanjaro is Africa's tallest freestanding mountain, meaning it rises dramatically from relatively flat surrounding terrain rather than being part of a larger mountain range. This makes Kilimanjaro particularly striking visually, as it dominates the landscape for miles around, its snow-capped summit visible from enormous distances across the East African plains. The mountain is actually a massive stratovolcano with three distinct volcanic cones: Kibo, Mwenzi, and Shira. Kibo, the highest of the three, hosts the summit known as Uhuru Peak, which in Swahili means Freedom Peak, a name chosen to commemorate Tanzania's independence. Though Kilimanjaro sits just 3 degrees south of the equator, in the heart of tropical Africa, its summit has been covered in ice and snow for thousands of years, creating that iconic image of snow-capped peaks rising above the African savanna. However, the mountain's glacier have been retreating rapidly in recent decades, shrinking by more than 80% since the early 20th century, a visible indicator of changing climate patterns that, as scientists concerned, the iconic snows of Kilimanjaro may disappear entirely within decades, transforming this legendary mountain and removing one of Africa's most distinctive natural features. When we talk about which mountain reaches farthest into space, the answer might surprise you. Mount Everest holds the record for highest elevation above sea level, but there's another mountain that can claim to reach farther from the center of the Earth, and that mountain is Mount Chimborazo in Ecuador. This snow-capped volcano, rising to 6,263 meters above sea level, is nearly 2.5 kilometers shorter than Everest, yet its summit is the point on Earth's surface that extends farthest from the planet's core. The reason for this apparent paradox lies in the shape of our planet itself. Earth is not a perfect sphere. It bulges slightly at the equator and is flattened somewhat at the poles, a shape caused by the planet's rotation. As Earth spins, centrifugal force pushes material outward most strongly at the equator, creating this equatorial bulge. The difference is surprisingly significant. The equatorial diameter of Earth is about 43 kilometers greater than the polar diameter. Chimborazo sits almost directly on the equator, at a latitude of just 1 degree south, which means it benefits fully from this equatorial bulge. When you measure from Earth's center rather than from sea level, Chimborazo's summit extends roughly 2,000 meters farther into space than Everest's does. So while Everest wins the race for altitude above sea level, Chimborazo wins if you're measuring which point gets you farthest from the planet's core, a reminder that even simple questions like which mountain is tallest can have multiple correct answers depending on how you define your terms. Turning our attention to Western Europe, the highest peak is Mont Blanc, that magnificent mountain that straddles the border between France and Italy. At 4,809 meters, Mont Blanc is not just the highest point in Western Europe but also one of the most iconic mountains in the world, its gleaming white summit a symbol of the Alps and of mountaineering itself. The name Mont Blanc means White Mountain in French, a reference to the permanent snow and ice that cover its upper reaches year-round. The mountain sits at the heart of the Mont Blanc Massif, a cluster of high peaks that form one of the most spectacular sections of the entire alpine range. Mont Blanc has a special place in mountaineering history, as its first ascent in 1786 by Jacques Balmat and Michel Paccard is often considered the birth of modern mountaineering as a sport. Before that successful climb, many people believed the high peaks of the Alps were unreachable, that the thin air and harsh conditions at such altitudes would kill anyone who attempted them. The successful ascent of Mont Blanc proved otherwise and sparked a golden age of alpine climbing that continues to this day. Now, hundreds of climbers attempt Mont Blanc every year during the summer season, following various routes to the summit, though the mountain still demands respect and claims lives regularly due to its unpredictable weather, hidden crevasses, and the simple challenges of altitude. At the opposite end of the Earth, in the frozen continent of Antarctica, the highest mountain is Vinson Massif, rising to 4,892 meters in the Sentinel Range of the Ellsworth Mountains. This remote peak was only discovered in 1957 and wasn't successfully climbed until 1966, making it one of the last major summits on Earth to be reached by humans. Vinson's late discovery and first ascent reflect just how isolated and inaccessible it is. Located deep in the interior of Antarctica, about 1,200 kilometers from the South Pole, Vinson sits in one of the coldest and most inhospitable environments on the planet. Temperatures on the mountain can plunge to -40 degrees Celsius or colder, and the perpetual daylight of the Antarctic summer, when climbing is possible, can be disorienting. Despite being the highest peak on the continent, Vinson is actually one of the easier climbs among the 7 summits, those highest mountains on each continent that ambitious mountaineers strive to climb. The main challenges are not technical climbing difficulties but rather the extreme cold, the logistics of reaching such a remote location, and the enormous expense involved in mounting an expedition to Antarctica. Still, Vinson has become increasingly popular in recent decades as commercial expedition companies have made it more accessible, at least for those with sufficient funds and determination. Back in the Himalayas, standing in the shadow of Everest, rises K2, the second highest mountain in the world at 8,611 meters. But don't let that second fool you into thinking K2 is somehow lesser than its more famous neighbor. In many ways, K2 is the more fearsome of the two, more difficult, more dangerous, more deadly. The mountain has earned the nickname Savage Mountain for good reason. K2 kills approximately 1 climber for every 4 who reach the summit, a fatality rate far higher than Everest's. The mountain is steeper than Everest, more prone to avalanches, and frequently battered by storms that can trap climbers for days or weeks. Unlike Everest, which has a relatively straightforward route on its south side that allows skilled climbers with good support to reach the summit, K2 has no easy path to the top. Every route is technically demanding, exposed to objective hazards like falling ice and rock, and subject to the severe weather that screams across the mountain with little warning. K2 has never been successfully climbed in winter, one of the last great challenges in mountaineering, though attempts continue. The mountain stands on the border between Pakistan and China in the Karakoram Range, and its pyramid-like form, viewed from the south, is one of the most aesthetically perfect mountain shapes in the world, beautiful and terrifying in equal measure. One curious fact about K2 is that it has no widely accepted local name, at least none that has become standard. Unlike Everest, which has traditional names in Nepali and Tibetan, or Denali, which bears its indigenous name, K2 is still known by its survey designation. The K stands for Karakoram, and the 2 indicates it was the second peak surveyed in that range during the Great Trigonometrical Survey of British India in the 19th century. The mountain's extreme remoteness is the reason for this absence of a local name. K2 is not visible from any inhabited valley. It sits deep in the mountains, surrounded by other high peaks, far from any settlements. The local Balti people who live in the region apparently had no specific name for it because they couldn't see it and had no reason to distinguish it from the many other distant peaks in their homeland. Several attempts have been made over the years to give K2 a proper name. Proposals like Mount Godwin Austen after an early surveyor, or Chagori, said to mean Great Mountain in Balti, but none have truly stuck. K2 remains K2, a designation that has taken on its own mystique, sounding almost extraterrestrial, perfectly fitting for a mountain that represents the absolute extreme of high-altitude mountaineering. Some mountains achieve fame not for their height but for their distinctive shape, and no mountain exemplifies this better than the Matterhorn. Standing on the border between Switzerland and Italy, the Matterhorn rises to 4,478 meters, making it far from the highest peak in the Alps. Yet it may be the most instantly recognizable mountain on Earth due to its near-perfect pyramid shape. When viewed from the Swiss town of Zermatt, the Matterhorn presents 4 steep faces oriented almost precisely toward the cardinal directions, converging at a sharp summit that seems to pierce the sky. This distinctive form has made the Matterhorn an icon, reproduced on everything from chocolate packages to movie studio logos. The mountain's shape is the result of specific geological processes, the intersection of rock layers and fault lines combined with erosional patterns that have carved the mountain into its present form. The Matterhorn was one of the last great alpine peaks to be climbed, not because it's the highest or even the most difficult, but because its steep faces and loose rock made it exceptionally dangerous. The first successful ascent in 1865 ended in tragedy when 4 of the 7 climbers fell to their deaths during the descent, an accident that shocked Europe and demonstrated that even successful climbs could end in disaster. Today, the Matterhorn remains a serious mountaineering challenge, its routes complicated by loose rock, frequent rockfall, and crowds of climbers that can create bottlenecks and hazards on the narrow ridges leading to the summit. If we're looking for extremes in mountain features, we should turn our attention to Mount Thor in Canada, which holds the record for the greatest vertical drop of any mountain on Earth. Located in Oyuatuk National Park on Baffin Island in the Canadian Arctic, Mount Thor features a vertical granite cliff face that drops 1,250 meters in a completely sheer, overhanging face. This isn't the height of the mountain itself, which rises to 1,675 meters above sea level, but rather the extent of its west face, a single unbroken cliff that falls away in an almost perfectly vertical to slightly overhanging wall. To put that in perspective, imagine a building roughly 370 stories tall, and then make it a single uninterrupted face of solid rock. The cliff averages an angle of about 105 degrees, meaning it actually overhangs, leaning outward as it rises. This makes Mount Thor's face not just the longest vertical drop, but also one of the most challenging big wall climbs in the world. The first ascent of the cliff face wasn't completed until 1985 and took a team of American and Canadian climbers 33 days of continuous climbing, living on the wall in portable ledges, hauling their gear up the seemingly endless expanse of granite. Mount Thor takes its name from the Norse god of thunder, and anyone who has stood at its base and looked up at that incomprehensible wall of stone would agree it's a fitting name for such an overwhelming natural feature. Still, Vinson has become increasingly popular in recent decades as commercial expedition companies have made it more accessible, at least for those with sufficient funds and determination. Back in the Himalayas, standing in the shadow of Everest, rises K2, the second highest mountain in the world at 8,611 meters. But don't let that second fool you into thinking K2 is somehow lesser than its more famous neighbor. In many ways, K2 is the more fearsome of the two, more difficult, more dangerous, more deadly. The mountain has earned the nickname Savage Mountain for good reason. K2 kills approximately one climber for every 4 who reach the summit, a fatality rate far higher than Everest's. The mountain is steeper than Everest, more prone to avalanches, and frequently battered by storms that can trap climbers for days or weeks. Unlike Everest, which has a relatively straightforward route on its south side that allows skilled climbers with good support to reach the summit, K2 has no easy path to the top. Every route is technically demanding, exposed to objective hazards like falling ice and rock, and subject to the severe weather that screams across the mountain with little warning. K2 has never been successfully climbed in winter, one of the last great challenges in mountaineering, though attempts continue. The mountain stands on the border between Pakistan and China in the Karakoram Range, and its pyramid-like form, viewed from the south, is one of the most aesthetically perfect mountain shapes in the world, beautiful and terrifying in equal measure. One curious fact about K2 is that it has no widely accepted local name, at least none that has become standard. Unlike Everest, which has traditional names in Nepali and Tibetan, or Denali, which bears its indigenous name, K2 is still known by its survey designation. The K stands for Karakoram, and the 2 indicates it was the second peak surveyed in that range during the Great Trigonometrical Survey of British India in the 19th century. The mountain's extreme remoteness is the reason for this absence of a local name. K2 is not visible from any inhabited valley. It sits deep in the mountains, surrounded by other high peaks, far from any settlements. The local Balti people who live in the region apparently had no specific name for it because they couldn't see it and had no reason to distinguish it from the many other distant peaks in their homeland. Several attempts have been made over the years to give K2 a proper name. Proposals like Mount Godwin Austen after an early surveyor, or Chagori, said to mean Great Mountain in Balti, but none have truly stuck. K2 remains K2, a designation that has taken on its own mystique, sounding almost extraterrestrial, perfectly fitting for a mountain that represents the absolute extreme of high-altitude mountaineering. Some mountains achieve fame not for their height but for their distinctive shape, and no mountain exemplifies this better than the Matterhorn. Standing on the border between Switzerland and Italy, the Matterhorn rises to 4,478 meters, making it far from the highest peak in the Alps. Yet it may be the most instantly recognizable mountain on Earth due to its near-perfect pyramid shape. When viewed from the Swiss town of Zermatt, the Matterhorn presents 4 steep faces oriented almost precisely toward the cardinal directions, converging at a sharp summit that seems to pierce the sky. This distinctive form has made the Matterhorn an icon, reproduced on everything from chocolate packages to movie studio logos. The mountain's shape is the result of specific geological processes, the intersection of rock layers and fault lines combined with erosional patterns that have carved the mountain into its present form. The Matterhorn was one of the last great alpine peaks to be climbed, not because it's the highest or even the most difficult, but because its steep faces and loose rock made it exceptionally dangerous. The first successful ascent in 1865 ended in tragedy when 4 of the 7 climbers fell to their deaths during the descent, an accident that shocked Europe and demonstrated that even successful climbs could end in disaster. Today, the Matterhorn remains a serious mountaineering challenge, its routes complicated by loose rock, frequent rockfall, and crowds of climbers that can create bottlenecks and hazards on the narrow ridges leading to the summit. If we're looking for extremes in mountain features, we should turn our attention to Mount Thor in Canada, which holds the record for the greatest vertical drop of any mountain on Earth. Located in Oyuatuk National Park on Baffin Island in the Canadian Arctic, Mount Thor features a vertical granite cliff face that drops 1,250 meters in a completely sheer, overhanging face. This isn't the height of the mountain itself, which rises to 1,675 meters above sea level, but rather the extent of its west face, a single unbroken cliff that falls away in an almost perfectly vertical to slightly overhanging wall. To put that in perspective, imagine a building roughly 370 stories tall, and then make it a single uninterrupted face of solid rock. The cliff averages an angle of about 105 degrees, meaning it actually overhangs, leaning outward as it rises. This makes Mount Thor's face not just the longest vertical drop, but also one of the most challenging big wall climbs in the world. The first ascent of the cliff face wasn't completed until 1985 and took a team of American and Canadian climbers 33 days of continuous climbing, living on the wall in portable ledges, hauling their gear up the seemingly endless expanse of granite. Mount Thor takes its name from the Norse god of thunder, and anyone who has stood at its base and looked up at that incomprehensible wall of stone would agree it's a fitting name for such an overwhelming natural feature. You can see this process in action if you watch clouds forming over a mountain range. They often appear seemingly out of nowhere on the windward side of the mountains, generated continuously as moist air is forced upward. The orographic lift effect is so powerful that some of the wettest places on Earth are mountain slopes positioned to intercept moisture-bearing winds. Mount Wailea in Hawaii receives an average of over 11 meters of rain per year, not because it's particularly tall, but because it sits directly in the path of the trade winds carrying moisture from the Pacific Ocean. The same process that creates abundant precipitation on one side of a mountain range simultaneously creates drought on the other side. As the air rises and cools on the windward side, dropping its moisture as rain or snow, it eventually crosses the summit and begins descending the leeward slope. As it descends, it compresses and warms, and warming air can hold more moisture. So instead of condensing into clouds and rain, any remaining water vapor stays gaseous and the clouds evaporate. The result is a rain shadow, a region downwind of mountains that receives far less precipitation than the windward side. Rain shadows can be extraordinarily pronounced. The Pacific Northwest coast of North America receives abundant rainfall, but just inland, on the eastern side of the Cascade Range, the landscape transforms into semi-arid shrubland, receiving only a fraction of the coastal rainfall. The Atacama Desert in Chile, one of the driest places on Earth, owes its extreme aridity largely to the rain shadow of the Andes Mountains, which block moisture from the Amazon basin to the east. Death Valley in California sits in the rain shadow of multiple mountain ranges, resulting in a place where rain is so rare that years can pass between measurable precipitation events. These rain shadows demonstrate how powerfully mountains control the distribution of water, creating lush forests on one side and deserts on the other, sometimes separated by only a few dozen kilometers. As you climb a mountain, you'll notice the air getting progressively colder, a phenomenon caused by what meteorologists call the lapse rate. In the troposphere, the lowest layer of Earth's atmosphere where weather occurs and where we live, temperature generally decreases with altitude at a fairly predictable rate. On average, the temperature drops about 6.5 degrees Celsius for every 1,000 meters you climb, though the exact rate varies depending on humidity and other factors. This cooling happens because air pressure decreases with altitude, and as air rises into lower pressure, it expands and cools, a fundamental principle of thermodynamics. This is why mountain peaks are cold even in tropical regions, why you need a jacket at high elevations even on a hot summer day, and why the highest mountains are capped with permanent snow and ice despite being on a planet where the average temperature is well above freezing. The lapse rate means that a tall mountain effectively contains multiple climate zones stacked vertically. You might start a climb in a warm valley with temperate forest, pass through zones of coniferous forest, then alpine meadows, and finally emerge onto barren rock and ice, traversing climate zones that would normally be separated by thousands of kilometers of latitude. This temperature gradient with altitude creates a natural boundary that's visible on mountains around the world. Above certain elevations, trees can no longer grow, not because they've run out of soil or water, but because the growing season becomes too short and the conditions too harsh for trees to survive. This boundary is known as the tree line or timberline, and it marks a dramatic transition in the mountain landscape. Below the tree line, forests cloak the mountainsides, but above it, only low-growing plants, grasses, mosses, and lichens can survive, creating the alpine zone that characterizes high mountain environments. The exact elevation of the tree line varies dramatically depending on latitude and local conditions. Near the equator, tree lines can be found at elevations exceeding 4,000 meters, while in subarctic regions, the tree line might occur at only a few hundred meters elevation. In some places near the poles, conditions are so harsh that trees can't grow even at sea level, and the tree line essentially merges with the Arctic tree line that marks the northern or southern limit of tree growth. The tree line isn't usually a sharp boundary but rather a transition zone called the Krummholz, a German word meaning crooked wood, where stunted, twisted trees battle against wind and cold, gradually giving way to treeless alpine terrain. Mountains create their own peculiar temperature phenomena beyond the simple lapse rate. In valleys and basins surrounded by mountains, particularly on clear, calm nights, cold air can pool in low-lying areas, creating temperature inversions. Normally, air temperature decreases with height, but during an inversion, the pattern reverses, with warmer air sitting on top of cooler air. This happens because cold air is denser than warm air, so it flows downhill like an invisible fluid, settling in valley bottoms and basins while warmer air remains at higher elevations. If you've ever camped in a mountain valley and woken to find frost covering your tent while the slopes above remain frost-free, you've experienced a temperature inversion. These inversions can be quite strong. Sometimes valley floors can be 15 or 20 degrees cooler than slopes just a few hundred meters higher. In populated mountain valleys, temperature inversions can trap air pollution near the ground, creating smog events that persist until weather conditions change enough to break up the inversion layer. Some mountain valleys are notorious for severe inversions. The valley around Salt Lake City, Utah, for example, is surrounded by mountains on all sides, creating a bowl that traps cold air and pollution during winter months, sometimes for days or weeks at a time. The ice and snow that characterize high mountain environments do more than just make mountains cold and beautiful. They actively reshape the landscape through the relentless work of glacier. These rivers of ice form when snow accumulates faster than it can melt, compressing under its own weight over decades and centuries until it transforms into dense glacial ice that begins to flow downhill under the pull of gravity. As glaciers move, they carve into the bedrock beneath them with incredible power, acting like enormous rasps that grind away at the mountain. Glaciers pluck rocks from the valley floor and walls, incorporating them into the ice, and these embedded rocks act as cutting tools, scouring and polishing the bedrock. Over thousands of years, glacier carve wide, U-shaped valleys into mountain landscapes, valleys with distinctive flat floors and steep, high walls that contrast sharply with the V-shaped valleys carved by rivers. When you see a valley with that characteristic U-shape, you're looking at the work of glacier, even if the ice itself disappeared thousands of years ago. Yosemite Valley in California is perhaps the most famous example of a glacially carved valley, its sheer granite walls plunging down to a wide, flat floor, the whole valley shaped by glacier that filled it during the ice ages. Similar U-shaped valleys appear in mountains worldwide, wherever glacier have done their patient, powerful work of reshaping the Earth. Mountains serve a purpose far more vital than simply being beautiful or challenging places to climb. They act as natural water towers for the planet, massive reservoirs that capture, store, and gradually release fresh water to the lowlands below. This function is so critical that it's not an exaggeration to say that mountains sustain much of life on Earth, not through any mystical quality, but through the simple physics of altitude, temperature, and precipitation. When moisture-laden air rises up mountain slopes, it cools and releases its water as rain at lower elevations and as snow higher up. This precipitation doesn't immediately run off into the valleys below. Instead, much of it is stored, temporarily frozen in snowpack during winter or locked away for years or centuries in glacier. Then, as temperatures rise with the changing seasons, this stored water is released gradually, melting over weeks or months and flowing down through mountain streams and rivers. This natural storage and release system is remarkably efficient, providing steady flows of water even during dry seasons when little or no precipitation falls. Without mountains to capture and store water, many regions would experience feast or famine hydrology, with floods during wet seasons and severe droughts the rest of the year. The glacier and snowpack on mountains feed major rivers worldwide, often rivers that flow through regions far from the mountains themselves. The great rivers of Asia, the Ganges, Brahmaputra, Indus, Yellow, and Yangtze, all originate in the Himalayas and the Tibetan Plateau, carrying meltwater from those high peaks down through the plains of India, Pakistan, China, and Southeast Asia. The Colorado River, which carved the Grand Canyon and supplies water to 7 U.S. states and Mexico, depends heavily on snowpack in the Rocky Mountains. The Rhine in Europe, the Murray-Darling in Australia, the Columbia in North America, these and countless other rivers owe their flows largely to mountain precipitation. Even rivers that don't originate directly in mountains often receive significant tributaries from mountainous regions. The Amazon, while largely a lowland river, receives contribution from Andean tributaries. This mountain water travels hundreds or thousands of kilometers from its source, supporting ecosystems and human populations far from the peaks where it fell as snow or rain. The dependence of humanity on mountain water is staggering when you examine the numbers. Over half of all people on Earth rely on water that originates in mountains for at least part of their water supply. Some estimates suggest that mountains provide between 60 and 80% of all the fresh water that flows into rivers and streams globally. Think about that for a moment. Despite covering only about a quarter of Earth's land surface, mountains generate the majority of usable fresh water. This isn't evenly distributed, of course. Some regions, like much of Central Asia, are almost entirely dependent on mountain water. Cities like Los Angeles, Denver, and Lima receive the overwhelming majority of their water from mountain sources. Agricultural regions in the rain shadows of mountain ranges, places that receive little direct precipitation, depend completely on irrigation water drawn from mountain-fed rivers. The connection between mountains and water security is so direct that changes to mountain hydrology, whether from reduced snowpack, retreating glacier, or altered precipitation patterns, can have immediate and severe consequences for billions of people living far downstream from the mountains themselves. Beyond their role as water towers, mountains are extraordinary reservoirs of biological diversity. Mountain ecosystems range from dense forests on lower slopes through various woodland zones and into alpine tundra near and above the tree line. Each elevation zone represents a distinct ecological community adapted to specific temperature ranges, precipitation levels, and growing season lengths. A single mountain can contain as many different ecosystems stacked vertically as you would encounter traveling thousands of kilometers from the equator toward the poles. This compression of climate zones creates conditions for exceptional biodiversity. Mountains worldwide host biodiversity hotspots, regions where unusually high numbers of species exist in relatively compact areas. The tropical Andes, the mountains of southwest China, the eastern Himalayas, these are among the most biodiverse regions on Earth, containing thousands of plant species, hundreds of bird species, and countless insects, amphibians, and mammals. The variety of microhabitats in mountains, different exposures to sun and wind, varying soil types, multiple elevation zones all packed together, creates opportunities for specialization and diversification that wouldn't exist in more uniform environments. What makes mountain biodiversity particularly significant is the high proportion of endemic species, organisms found nowhere else on Earth. Mountain ranges, particularly isolated ones, function as what biologists call islands in the sky for evolution. Just as oceanic islands develop unique species because their isolation prevents genetic mixing with mainland populations, mountaintops separated by low elevation valleys or plains can become isolated biological islands where species evolve independently. A species adapted to cool, moist conditions at high elevation cannot easily disperse to another mountain range if the intervening lowlands are hot and dry. Over thousands or millions of years, this isolation allows populations on different mountains to diverge, eventually becoming distinct species. The result is that many mountain ranges host species found nowhere else. The Ethiopian highlands are home to the gelada baboon, found only there. The mountains of Madagascar contain species of lemurs unique to specific mountain ranges. The Sierra Nevada of California hosts plants and animals that exist nowhere else. This pattern repeats worldwide, making mountains irreplaceable reservoirs of evolutionary diversity, biological libraries that cannot be replicated elsewhere. During the brief mountain summers, alpine meadows explode into bloom in a spectacular display of life, making the most of limited opportunity. In these high-elevation environments above the tree line, the growing season might last only a few weeks or months, bookended by the long winter when the ground is frozen and snow-covered. Plants in these environments must complete their entire annual cycle, germination, growth, flowering, and seed production, in this narrow window. The result is that when conditions are right, alpine meadows can become carpeted with wildflowers, entire hillsides painted in waves of color as different species bloom in succession. These alpine plants often grow in low, compact forms, hugging the ground to escape the wind and to take advantage of the slightly warmer temperatures right at the soil surface. Many are perennials that store energy in roots or bulbs underground, allowing them to begin growing quickly when the snow melts rather than starting from scratch each year. The flowers themselves are often disproportionately large and brightly colored relative to the small size of the plants, adaptations to attract the limited pollinators available in these harsh environments. Anyone who has witnessed an alpine meadow in full bloom will attest to the beauty and the sense of urgency these displays convey, as if the plants know their time is precious and must make the most of every moment of summer. Mountains are also serving as early warning systems for climate change, and the signals they're sending are increasingly urgent. Species shifts upslope, where plants and animals move to higher elevations in response to warming temperatures, reveal some of the clearest evidence that climates are changing. Researchers studying mountain ecosystems have documented this phenomenon worldwide. The tree line is moving higher on many mountains as trees colonize areas that were previously too cold. Alpine plant species are migrating upslope, sometimes at rates of several meters per decade, tracking the climate conditions they're adapted to as those conditions move higher. Animals too are shifting their ranges upward. Studies in the Sierra Nevada, the Alps, the Andes, and elsewhere have found birds, mammals, and insects that now occupy higher elevation ranges than they did just a few decades ago. This upslope migration is a direct response to temperature increase. As the climate warms, the temperature conditions that define a particular elevation zone effectively move upward, and species adapted to those conditions follow. The problem is that mountains have tops. Species can only move upslope so far before they run out of mountain. Those already at or near the summit have nowhere to go, and as conditions continue warming, they face increasing stress and potential extinction. Mountain specialists, species highly adapted to the coldest, highest environments, are particularly vulnerable. They're being squeezed into smaller and smaller areas as the climate zones they depend on shrink toward the mountain peaks. When scientists calculate Earth's biodiversity and map where species live, mountains emerge as disproportionately important. Despite covering roughly a quarter of the planet's land surface, mountains host a significant portion of global biodiversity that far exceeds what their area alone would suggest. The vertical stratification of mountain environments, with their stacked climate zones and varied microclimates, creates conditions that support remarkable numbers of species. Mountains contain a substantial portion of the world's amphibians, those sensitive creatures that require specific moisture and temperature conditions and often cannot survive in the hot, dry lowlands. Birds find in mountains a diversity of habitats from tropical forests at lower elevations to alpine tundra higher up, and many bird species are restricted to specific elevation ranges on specific mountain systems. Mammals too are exceptionally diverse in mountains, from small rodents adapted to high-altitude life to large predators like snow leopards and mountain lions that roam across elevation zones. The importance of mountains for biodiversity extends beyond just the number of species. Many of these mountain species are highly specialized, adapted to narrow niches that exist only in particular mountain environments. This makes them irreplaceable, unique expressions of evolution that could not exist anywhere else and could not be recreated if lost. Mountains are not just refuges for wildlife, they're also home to people, and a surprising number of people at that. About 10 to 15% of the world's population lives in mountain regions, somewhere between 800 million and over 1 billion people depending on exactly how you define mountain areas. These mountain dwellers are found on every inhabited continent, from the high valleys of the Andes to the terrace slopes of the Himalayas, from the Alps of Europe to the highlands of East Africa. Mountain life presents unique challenges. The terrain is often steep and difficult to farm, the climate harsh with short growing seasons, and mountain communities can be isolated, sometimes cut off from lowland areas by snow for months each year. Yet people have not just survived in these environments, they've thrived, developing sophisticated strategies for living with the mountains. Terraced agriculture transforms steep slopes into productive farmland. Traditional mountain architecture uses local materials and designs adapted to withstand heavy snow loads and strong winds. Mountain peoples have bred specialized crops and livestock varieties suited to high-altitude conditions, from the potatoes of the Andes that grow at elevations where most crops fail, to the yaks of Tibet that thrive in thin air where cattle struggle. Mountain communities often develop unique cultures and languages, another expression of the isolating effect of mountain topography. When valleys are separated by high passes that are difficult or impossible to cross for much of the year, the populations in those valleys tend to develop independently, their languages diverging over time, their customs and traditions taking on distinctive characteristics. The result is that mountain regions worldwide are patchworks of cultural and linguistic diversity. The Caucasus Mountains, that relatively small range between the Black and Caspian Seas, is home to dozens of distinct ethnic groups speaking languages from multiple unrelated language families. The highlands of Papua New Guinea contain such extreme linguistic diversity that villages separated by just a few kilometers may speak mutually unintelligible languages. The mountain regions of the Himalayas host a mosaic of cultures, from the Sherpa of Nepal to the various Tibetan groups, each with their own dialects, traditions, and ways of relating to their mountain environment. This cultural diversity mirrors the biological diversity of mountains, both products of the way mountains fragment landscapes and create isolated pockets where separate evolutionary or cultural trajectories can unfold. Throughout human history, mountains have been more than just physical features or places to live. They've held deep spiritual and religious significance for cultures worldwide. Sacred mountains appear in myths and religions across civilizations, often serving as the dwelling places of gods, the centers of the cosmos, or bridges between the earthly and divine realms. There's something about mountains, their height, their permanence, their tendency to disappear into clouds as if reaching beyond the visible world, that seems to invite this kind of spiritual interpretation. Mountains stand apart from the ordinary landscape, special places that demand respect and wonder. In an age before air travel, mountain peaks were quite literally the closest points on Earth to the heavens, the places where Earth and sky came nearest to touching. It's perhaps not surprising that so many cultures imagined their gods dwelling on these high places, looking down on the human world from peaks that humans could barely reach. In ancient Greek mythology, Mount Olympus was believed to house the gods themselves, the pantheon of deities ruled by Zeus living in palaces atop Greece's highest mountain. The peak of Olympus, often shrouded in clouds, was imagined as the throne room of Zeus, from which he could hurl thunderbolts and observe all of Greece spread below. The gods would gather on Olympus for councils and feasts, and occasionally descend to interfere in human affairs before returning to their mountain home. This mythological geography had a physical anchor. Mount Olympus is a real mountain, rising nearly 3,000 meters on the border between Thessaly and Macedonia. Ancient Greeks could see it, could observe its cloud-wrapped summit, and could imagine what divine realm might exist in that inaccessible height. The association between Olympus and the gods was so strong that when the Greeks colonized other regions, they sometimes named local mountains Olympus, as if the name itself carried sacred power. The idea that divinity dwells on mountaintops is not unique to Greece. Many cultures have their sacred mountains, but Olympus may be the most famous example, the archetype that still influences how we think about the relationship between height and holiness. In Japan, Mount Fuji holds spiritual significance that extends back centuries and remains powerful today. This nearly perfect volcanic cone, rising in graceful symmetry to 3,776 meters, has been considered sacred in both Shinto and Buddhist traditions. Fuji is seen as the dwelling place of kami, the spirits or gods of Shinto belief, and has been a destination for pilgrims for over 1,000 years. The mountain appears countless times in Japanese art and literature, its iconic form instantly recognizable as a symbol not just of natural beauty but of Japanese identity itself. Climbing Mount Fuji has traditionally been undertaken as a spiritual practice, not merely a recreational activity. Pilgrims would dress in white, the color of purity, and would climb during the short summer season when the mountain is relatively free of snow, often timing their ascent to reach the summit at dawn to witness the sunrise from the top of Japan's most sacred peak. Even today, when hundreds of thousands of people climb Fuji each year, many still approach the climb with a sense of reverence, and Shinto shrines dot the climbing routes. The mountain was added to UNESCO's World Heritage List not primarily for its natural features but as a cultural landscape, recognition that Fuji's significance lies as much in its spiritual and cultural meaning as in the physical mountain itself. Perhaps no mountain on Earth is held as sacred by as many different religious traditions as Mount Kailash, a peak in Tibet rising to 6,638 meters. Kailash is sacred to Hinduism, Buddhism, Jainism, and the ancient Tibetan Bon religion, a remarkable convergence of spiritual significance. In Hindu tradition, Kailash is the home of Lord Shiva and his consort Parvati, the center of the universe where Shiva sits in eternal meditation. For Buddhists, Kailash is the home of the Buddha Demchok, representing supreme bliss. Jains believe it to be the place where the founder of their religion attained liberation. The Bon tradition considers it the seat of all spiritual power. This multifaceted sacred status makes Kailash one of the most important pilgrimage destinations in Asia. Pilgrims come from across India, Tibet, Nepal, and beyond to visit the mountain, undertaking journeys that can take weeks or months to complete. What makes Mount Kailash unique among major sacred mountains is how pilgrims interact with it. Rather than climbing to the summit, as pilgrims might at other sacred mountains, those who come to Kailash circle it, performing what's called a kora or parikrama, a circumambulation of the mountain. The circuit around Kailash is about 52 kilometers and involves crossing a high pass at over 5,600 meters elevation. Pilgrims, including many who prostrate themselves for the entire circuit, a process that can take weeks, believe that completing the circuit brings spiritual merit and purification. Some devout practitioners complete the circuit 108 times, a number sacred in both Hinduism and Buddhism. The practice of circling rather than climbing is deeply rooted in the belief that the mountain is too sacred to be stepped upon, that to climb it would be an act of profound disrespect to the divine. This tradition is so strong that even in the modern era of mountaineering, when virtually every major peak on Earth has been climbed, Mount Kailash remains unclimbed. No one has ever officially climbed Mount Kailash, a remarkable distinction for a mountain that is not technically difficult by mountaineering standards. The mountain's pyramid-like shape and steep faces would present challenges, certainly, but nothing that modern climbers with proper equipment couldn't overcome if permitted to try. The reason Kailash remains unclimbed is respect for its sacred status. The Chinese government, which controls the region where Kailash is located, has never granted permission for a climbing attempt, recognizing that doing so would deeply offend the religious sensibilities of millions of people across multiple faiths. There have been offers, including from wealthy mountaineers willing to pay substantial sums for permission to climb, but these have been refused. In 2001, when the Chinese government reportedly considered granting permission to a Spanish expedition, the outcry from religious communities was so intense that the plan was abandoned. Mount Kailash thus stands as a testament to the power of the sacred, a peak that remains inviolate not because it cannot be climbed, but because it should not be, a place where spiritual and cultural values have successfully protected a mountain from the human impulse to conquer every summit. The idea of climbing mountains purely for the challenge and experience is surprisingly recent in human history. Mountaineering as we know it, the sport of climbing peaks for their own sake, emerged as a distinct activity only in the mid-19th century. Before that time, people certainly crossed mountains when necessary, shepherds climbed high slopes to tend their flocks, and hunters pursued game into mountainous terrain. But the notion of climbing a difficult peak simply because it was there, simply for the achievement and the experience, was largely foreign to most cultures. Mountains were obstacles to be avoided or crossed efficiently, not destinations in themselves. The shift began in Europe, particularly in the Alps, during the late 18th and early 19th centuries as a cultural movement called Romanticism began celebrating wild nature and sublime landscapes. Mountains, which had previously been seen as frightening, chaotic places, began to be viewed as beautiful and spiritually elevating. Scientists also became interested in mountains, wanting to study geology, glaciology, and the effects of altitude. These twin impulses, the aesthetic and the scientific, combined with a growing middle class that had leisure time and disposable income, creating conditions for mountaineering to emerge as an organized pursuit. Early climbers often sought escape from the rapidly industrializing cities of Europe and North America. The 19th century saw unprecedented urbanization as the Industrial Revolution drew people from rural areas into crowded cities filled with factories, smoke, and noise. For people living in these conditions, mountains represented everything the city was not: pure, pristine, uncrowded, challenging in natural rather than social ways. Climbing offered both physical challenge and spiritual renewal, a chance to test oneself against nature rather than simply working in a factory or office. The golden age of alpine mountaineering, roughly the 1850s through the 1860s, saw the first ascents of most major alpine peaks by climbers who were often educated professionals, lawyers, scientists, clergy, seeking adventure and escape during their holidays. Edward Whymper, who made the first ascent of the Matterhorn, was an engraver and illustrator. John Tyndall, who made numerous important first ascents in the Alps, was a physicist. These weren't professional athletes but enthusiastic amateurs for whom climbing represented a profound counterpoint to their workaday lives in Victorian civilization. The measurement of mountain heights before modern technology was a remarkable feat of mathematical and surveying ingenuity. Before GPS and satellite technology made it possible to determine elevations with extraordinary precision, mountains were measured using triangulation, a method that uses trigonometry to calculate distances and heights. Surveyors would establish a baseline, a carefully measured distance between 2 points, and would then measure the angles from each end of this baseline to the mountain peak. With the baseline distance and the two angles, they could calculate the distance to the peak using trigonometry. Then, by measuring the angle of elevation from known points, they could calculate the height. This sounds straightforward, but in practice it was incredibly difficult. Measurements had to be taken from great distances because surveyors needed to see the peaks from the lowlands where they could establish their baselines. Even small errors in angle measurements could lead to significant errors in the calculated height. Atmospheric refraction, where light bends as it passes through air of varying density, could throw off measurements. And all of this work had to be done with theodolites and other instruments that, while sophisticated for their time, were primitive compared to modern equipment. The first measurements of Mount Everest height were made in the 1850s as part of the Great Trigonometrical Survey of British India, a decades-long project to map the Indian subcontinent. When the calculations were complete, they showed Everest height as 8,840 meters, or 29,002 feet. However, the height was deliberately reported as an odd number, 8,848 meters, or 29,029 feet. Why add 8 meters to the calculated height? The surveyor in charge, Andrew Waugh, was concerned that if he reported the height as exactly 8,840 meters, people would think it was just a round number estimate rather than a precise measurement. So he added a small amount to make the number seem more precise, more like a genuine measurement rather than an approximation. It's a delightful bit of historical irony that the adjustment made to demonstrate precision was itself an imprecise fudging of the numbers. Modern measurements using GPS and other technologies have since determined that Everest height is indeed 8,848 meters, remarkably close to that 19th century calculation, though the coincidence between the adjusted historical figure and the modern measurement is just that, coincidence. Today, Mount Everest has become the ultimate mountaineering destination, the peak that captures global imagination more than any other. Each year, about 1,200 people attempt to climb Everest, most during the brief windows in May and sometimes in September or October when weather conditions on the mountain are relatively favorable. This is a dramatic increase from earlier decades. In 1953, when Edmund Hillary and Tenzing Norgay made the first confirmed ascent, they were part of a large expedition, but they were the only two to reach the summit that year. Through the 1960s, 70s, and 80s, only a few dozen people reached Everest's summit each year. But commercialization of Everest climbing, where guide companies offer packages that include everything from permits to Sherpa support to bottled oxygen, has made the mountain accessible to anyone with sufficient money and basic fitness, even if they lack extensive mountaineering experience. The result has been a surge in attempts and a troubling crowding problem, with hundreds of climbers sometimes queuing at bottlenecks on the route, waiting their turn to proceed while exposed to extreme cold and altitude. Despite all the infrastructure and support now available on Everest, the mountain remains brutally difficult and dangerous. Only about half of those who attempt Everest successfully reach the summit in any given year. The other half turn back, either due to weather, equipment problems, altitude sickness, or simply because they reach their physical or mental limits. Turning back is often the right decision, the wise decision that saves lives, but it can be psychologically devastating for people who have spent tens of thousands of dollars and months of their lives preparing for the attempt. The summit success rate varies year to year depending on weather conditions and other factors, but it rarely exceeds 60% and is often closer to 50% or lower. And these statistics only count those who make serious summit attempts. Many climbers never get that far, turning back at lower camps or not even making it to base camp due to altitude-related illness. The death toll on Everest is a grim reminder that despite all the commercialization and support, this remains an incredibly dangerous mountain. Over 300 people have died attempting to climb Everest since records began, and hundreds of climbers' bodies remain preserved on the mountain, frozen in the positions where they fell. The extreme cold at high altitude essentially freeze-dries bodies, preserving them for decades. Many of these bodies are in locations that are too dangerous to reach for recovery, or where the effort required to bring them down would endanger the lives of others. Some bodies have become landmarks on the routes, grim signposts that climbers pass on their way up and down. One section of the mountain has acquired the darkly poetic name Rainbow Valley, not because of any natural beauty but because it's named for the brightly colored jackets on frozen corpses visible along the route. Modern mountaineering gear comes in vivid colors, reds, yellows, blues, and greens, making climbers more visible and safer, but these same colorful jackets now mark the locations where people died, creating a grotesque rainbow of death in the snow. The reason Everest and other high peaks are so deadly becomes clear when you understand what happens to the human body at extreme altitude. Above approximately 8,000 meters, or 26,000 feet, lies what mountaineers call the death zone, an altitude where the human body simply cannot survive for extended periods. At this height, the air pressure is so low that there isn't enough oxygen for the body to function normally. Even while breathing bottled oxygen, climbers in the death zone are barely maintaining themselves. Without supplemental oxygen, most people would lose consciousness within minutes and die shortly thereafter. The body begins to deteriorate almost immediately upon entering the death zone. Cells start dying from oxygen starvation. The digestive system essentially shuts down, making it nearly impossible to digest food, so climbers cannot replenish the energy they're burning. Sleep becomes impossible or nearly so, as the body struggles to maintain basic functions. Mental clarity deteriorates, judgment becomes impaired, and climbers can make fatal decisions simply because their brains aren't functioning properly. Every moment spent in the death zone is borrowed time, which is why summit attempts from the highest camps must be completed quickly. Climbers typically leave their highest camp around midnight, climbing through the night and early morning to reach the summit around dawn, then descending as quickly as possible. Even with this rushed schedule, climbers often spend 10 to 16 hours in the death zone during a summit attempt, and every hour increases the risk. The human body deteriorates rapidly at such altitudes, and the longer you stay, the more likely something will go wrong. Frostbite, snow blindness, altitude sickness, exhaustion, any of these can turn lethal in an environment where there's no margin for error and where the simple act of moving forward requires every bit of willpower and physical capacity a person possesses. The death zone is a realm where human beings simply do not belong, where we can visit briefly but cannot remain, a hostile environment that reminds us that despite all our technology and determination, there are places on Earth where we survive only as temporary intruders. As climbers ascend into higher elevations, their bodies begin to struggle with a fundamental challenge that has nothing to do with steep slopes or dangerous terrain. The air itself becomes the enemy through a condition known as altitude sickness. This malady affects climbers above approximately 8,000 feet, or about 2,400 meters, though some people can experience symptoms at even lower elevations while others remain unaffected until much higher. Altitude sickness occurs because air pressure decreases with elevation, and lower air pressure means less oxygen is available with each breath. At 8,000 feet, there's only about 75% as much oxygen available as at sea level. The body responds to this oxygen deficit in various ways, some helpful and some decidedly not. Blood vessels in the brain can swell, causing the throbbing headaches that are often the first sign of altitude sickness. The digestive system rebels, leading to nausea and loss of appetite. Sleep becomes difficult, breathing irregular. In more severe cases, fluid can accumulate in the lungs or brain, conditions called high-altitude pulmonary edema and high-altitude cerebral edema, both of which can be rapidly fatal if the person doesn't descend immediately. The symptoms of altitude sickness can range from merely uncomfortable to life-threatening. Headaches are almost universal, often described as the worst headache sufferers have ever experienced, a deep, pounding pain that doesn't respond well to ordinary painkillers. Nausea can make eating impossible at exactly the time when climbers need energy most. Confusion is particularly dangerous because it impairs judgment at a time when good decisions are critical. A confused climber might continue upward when they should retreat, or might wander off route into dangerous terrain. They might fail to recognize their own symptoms, insisting they're fine when they're clearly deteriorating. Other symptoms include extreme fatigue, dizziness, shortness of breath even at rest, and difficulty sleeping. The insidious thing about altitude sickness is that it can strike anyone regardless of fitness level. An Olympic athlete can be laid low while a sedentary person might barely notice the altitude. The only reliable prevention is gradual acclimatization, giving the body time to adjust by ascending slowly and spending time at intermediate elevations before going higher. Beyond the invisible threat of altitude sickness, mountains present very visible dangers, and few are more terrifying than avalanches. These cascades of snow thundering down mountainsides pose one of the deadliest mountain hazards, killing dozens to hundreds of people worldwide each year. Avalanches occur when the snow on a slope becomes unstable, often because a weak layer exists beneath stronger layers, creating a structure waiting to collapse. The trigger can be additional snowfall adding weight, warming temperatures weakening the bonds between snow crystals, or simply a climber or skier crossing the slope and breaking the delicate balance. Once started, an avalanche can accelerate to speeds exceeding 130 km per hour, carrying thousands of tons of snow with the force of a freight train. Being caught in an avalanche is like being tumbled in a massive washing machine filled with concrete, survivors describe it. The snow batters you, disorients you, and when it finally stops, it often sets up like cement, making it nearly impossible to dig yourself out. The sheer frequency of avalanches in mountain regions is staggering. One researcher working in the Swiss Alps recorded over 17,000 avalanches in a single year of observation. That's an average of more than 46 avalanches every single day in just one mountain region. Most of these are small, harmless slides in uninhabited areas, but the numbers illustrate just how dynamic and unstable snow-covered slopes can be. Mountains are constantly shedding snow through countless small and large avalanches, a natural process of clearing accumulated snow from steep slopes. The problem arises when people put themselves in avalanche terrain, whether climbing, skiing, or living in mountain valleys. Historic records show that avalanches have destroyed entire villages. In 1916, an avalanche in the Italian Alps killed more than 300 people when it obliterated the village of Marmolada. In 1970, an earthquake in Peru triggered an avalanche that swept down from Huascaran, burying the town of Yungay and killing an estimated 18,000 people in a matter of minutes. Perhaps the most shocking avalanche statistics come from World War I, when Austrian and Italian forces fought each other in the Alps, building fortifications and trenches at high altitude and shelling enemy positions in the mountains. The warfare itself took thousands of lives, but avalanches were even more deadly. Nearly half of the troops deployed in alpine zones during World War I died in avalanches, not from enemy action. Some of these avalanches were natural, triggered by the weight of snow or by temperature changes. But others were deliberately triggered by artillery fire. Both sides would shell the slopes above enemy positions, hoping to trigger avalanches that would sweep away enemy troops. Soldiers lived in constant fear not just of bullets and bombs but of the mountains themselves. Tens of thousands of men were buried in snow, their bodies often not recovered until decades later when glacier finally released them. The mountains of the Alps still occasionally give up remains from that terrible conflict, soldiers emerging from melting ice a century after they died. Mountains have witnessed countless personal tragedies and triumphs, and few climbing achievements are as poignant as Reinhold Messner's solo ascent of Nunga Parbat. Messner, who would go on to become perhaps the greatest high-altitude mountaineer of all time, the first person to climb all 14 8,000-meter peaks, had a complicated history with Nunga Parbat, the 9th highest mountain in the world. In 1970, Messner and his younger brother Gunther climbed the Rupal face of Nunga Parbat together, reaching the summit. But during the descent, disaster struck. Gunther died, either in an avalanche or from altitude-related illness and a fall. The exact circumstances remain disputed. Reinhold barely survived the descent, suffering severe frostbite that cost him 7 toes. The tragedy haunted him, and accusations from other expedition members that he had abandoned his brother added to the psychological burden. In 1978, Messner returned to Nunga Parbat and climbed it solo, without supplemental oxygen, via a new route, a feat considered impossible by most mountaineers. It was simultaneously a remarkable athletic achievement and an act of personal redemption, a way of confronting the mountain that had taken his brother and nearly killed him. Sometimes the very act of studying mountains can prove fatal, as happened to the man for whom Mount Mitchell is named. Elisha Mitchell was a professor and scientist in North Carolina who spent years surveying the mountains of the region, trying to determine which peak was the highest. In the mid-19th century, there was a dispute about whether the peak now called Mount Mitchell or a nearby peak called Clingman's Dome was higher. Mitchell was convinced his measurements were correct and his peak was taller. In June 1857, he returned to the mountains to verify his measurements. He never returned from that trip. His body was found at the base of a waterfall, where he had apparently slipped and fallen while trying to navigate difficult terrain in stormy weather. The tragic irony is that Mitchell was right. His peak is indeed the highest point in the eastern United States at 2,037 meters, and it now bears his name, a memorial to a scientist who died in pursuit of accurate knowledge about the mountains he studied. Mountains are slowly eroding away all the time, but occasionally pieces fall off in dramatic fashion. A chunk of Mont Blanc summit, weighing several hundred kilograms and measuring roughly 50 centimeters across, is now preserved in a museum, an unusual souvenir of mountain geology. This piece of Mont Blanc didn't fall naturally but was deliberately removed during a scientific expedition studying the mountain. It represents actual summit rock from Western Europe's highest peak, a tangible piece of a place that few people ever reach. Having such a specimen in a museum allows scientists to study the rock composition and allows the public to quite literally touch a piece of history and geology that would otherwise be completely inaccessible. The rock tells a story of mountain building, of tectonic forces that pushed ancient seafloor sediments upward into the sky, of the subsequent weathering and erosion that shaped the peak into its current form. Not all changes to mountains are so deliberate or small-scale. Araki/Mount Cook, New Zealand's highest peak, lost significant height due to a massive rockfall in December 1991. The mountain, which had stood at 3,764 meters, lost approximately 10 meters of elevation when a huge section of the summit collapsed and avalanched down the mountain's northeast face. In an instant, the mountain became shorter, dropping to about 3,754 meters. The collapse involved an estimated 10 to 12 million cubic meters of rock and ice, one of the largest rockfalls in New Zealand's recorded history. The event dramatically reshaped the summit area and altered climbing routes on the mountain. It also served as a reminder that mountains, despite appearing solid and eternal, are actually dynamic features constantly being reshaped by geological processes. Rock is slowly weakened by freeze-thaw cycles, by water infiltration, by the simple effects of gravity over time, and eventually sections fail and fall. Every mountain is slowly destroying itself, wearing away grain by grain or, occasionally, in massive catastrophic collapses. Mountain names themselves can be as changeable as the mountain's physical forms, and some mountain names have changed repeatedly due to politics, reflecting the human conflicts and shifting power dynamics that swirl around these seemingly timeless natural features. Mount McKinley became Denali, then officially became Denali in the United States after decades of debate. Everest itself is known by different names to different people, Sagarmatha in Nepal and Chomolungma in Tibet, and there have been periodic calls to officially change the name to one of these indigenous names rather than keeping the name given by British surveyors after George Everest. In Africa, Kilimanjaro has kept its name, but nearby Mount Kenya was renamed from Mount Kirinya by British colonizers before being changed back. In the Caucasus, peaks have changed names as borders shifted and political systems changed. What was called Stalin Peak in the Soviet era became Communism Peak and is now known as Ismail Simoni Peak in Tajikistan. These naming disputes remind us that while the mountains themselves exist outside of human politics, our relationship with mountains, how we name them, who claims them, what they symbolize, is deeply political and cultural, reflecting our need to make these grand natural features part of our own human narratives. Throughout history, mountains have attracted not just explorers and pilgrims but storytellers and mythmakers, people seeking to explain the world through legend and tradition. Mount Ararat, that dramatic twin-peaked volcano rising in eastern Turkey near the Armenian border, is traditionally linked to one of the most famous stories in Western religious tradition, that of Noah's Ark. According to the Book of Genesis, after the great flood that covered the earth, Noah's Ark came to rest on the mountains of Ararat. For centuries, this has led to speculation and numerous expeditions searching for remains of the Ark on the mountain slopes. Mount Ararat rises to over 5,000 meters, its summit covered in permanent snow and ice, and various explorers have claimed to find wooden structures or anomalies that might be the Ark. None of these claims have been substantiated, and most scholars view the flood narrative as mythological rather than historical, but the association between Ararat and the Ark remains powerful. The mountain itself straddles complex political and cultural territory, visible from Armenia where it holds deep national significance despite being located in Turkey, a reminder of how mountains can become symbols that transcend borders. In Switzerland, Mount Pilatus overlooks Lake Lucerne, its dramatic rocky peaks dominating the landscape. This mountain carries its own dark legend, said to be the burial site of Pontius Pilate, the Roman governor who, according to the New Testament, ordered the crucifixion of Jesus. Medieval legend claimed that after Pilate's death, his troubled spirit was condemned to wander, and his body was eventually thrown into a small lake on the mountain, thereafter called Pilatus after the haunted governor. The legend warned that anyone who disturbed the lake would unleash terrible storms and disasters. For centuries, climbing the mountain was actually forbidden by local authorities who feared angering Pilate's ghost. It wasn't until the 16th century that a local clergyman deliberately climbed to the lake and demonstrated that nothing terrible happened, gradually breaking the superstitious hold the legend had on the local population. Today, Mount Pilatus is a popular tourist destination, accessible by the world's steepest cogwheel railway, but the name preserves that medieval legend, a reminder of when mountains were seen as mysterious and potentially dangerous places where supernatural forces might dwell. The Himalayas have given birth to their own legendary creature, the Yeti, also known as the abominable snowman, said to roam the high mountains of Nepal, Tibet, and Bhutan. Described as a large, ape-like creature covered in white or reddish-brown fur, the Yeti appears in local folklore and has captured the imagination of Westerners since the early 20th century, when mountaineering expeditions began bringing back stories of mysterious footprints in the snow and accounts from local people who claim to have seen the creature. Numerous expeditions have searched for evidence of the Yeti, examining footprints, collecting hair samples, and investigating supposed Yeti scalps kept in monasteries. Scientific analysis has repeatedly shown that the evidence points to known animals, bears, wolves, or misidentified human tracks, but the legend persists. The Yeti has become a cultural icon, appearing in countless books, movies, and television shows, evolving from a figure of local folklore into a global phenomenon. Whether the Yeti exists or not, and the scientific consensus is firmly on the side of not, the legend speaks to something deeper, our fascination with the unknown, with the possibility that remote mountains might still hide secrets, that there might be places wild enough and remote enough to shelter creatures science hasn't yet documented. Some mountains accumulate religious significance across multiple traditions, becoming shared sacred sites that transcend sectarian boundaries. Sripada, also known as Adam's Peak, in Sri Lanka is one such place. This distinctive cone-shaped mountain rises 2,243 meters and features at its summit a rock formation resembling a large footprint. Buddhists believe this is the footprint of Buddha, left when he visited the island. Hindus identify it as the footprint of Shiva. Muslims believe it's where Adam first set foot on earth after being expelled from paradise, hence the name Adam's Peak. Some Christians have associated it with Saint Thomas, who is said to have brought Christianity to India. For centuries, pilgrims from all these traditions have climbed the mountain, especially during the pilgrimage season from December to May, ascending thousands of steps in the darkness to reach the summit for sunrise. The mountain represents a rare point of religious harmony, where different faiths peacefully share a sacred site, each bringing their own interpretation to the mysterious footprint while respecting the devotion of others. Other mountains enforce strict religious codes that can seem startling to modern sensibilities. Mount Athos, a peninsula in northern Greece that rises to over 2,000 meters, bans women from entering its territory due to ancient monastic traditions dating back over 1,000 years. The entire peninsula is essentially a monastic republic, home to 20 Orthodox Christian monasteries that govern themselves with a degree of autonomy from the Greek state. The ban on women, called the avatun or garden closed to the impure, officially extends to all female mammals, though in practice female cats and chickens are present. The justification given by the monks is that the Virgin Mary is considered the spiritual patroness of Mount Athos, and out of respect for her, no other women should set foot there. The ban has been controversial, challenged by the European Union and women's rights advocates as discriminatory, but it remains in force, protected by Greek law and a special provision in the treaty that admitted Greece to the European Union. Mount Athos represents a rare survival of medieval monastic tradition into the modern world, a place where time seems to have stopped centuries ago, though whether that's admirable or problematic depends largely on one's perspective. Mountains have long been sites of religious and political power, places where elites retreated for spiritual practices or to oversee their domains. Huayna Picchu, the distinctive peak that looms behind the famous ruins of Machu Picchu in Peru, once housed Incan religious elites who lived and worshipped in structures built into the mountain's steep slopes. The peak rises about 2,700 meters above sea level, roughly 360 meters above the main Machu Picchu site, and reaching its summit requires climbing steep stone stairs built by the Inca, some sections so precipitous that modern visitors must use cables for safety. At the summit and on terraces carved into the mountainside are the remains of temples and residential structures where priests and nobility lived, performing ceremonies and maintaining the sacred geography of this high Andean site. The Inca were master mountain architects, building structures that seemed to grow organically from the rock, perfectly fitted stonework that has survived earthquakes that would have leveled more crudely built structures. Huayna Picchu demonstrates how mountains could serve as both fortress and temple, combining defensive advantages with spiritual significance, places where those in power could literally look down upon the world while being closer to the heavens. Some mountains offer perspectives that seem to compress an entire landscape into a single panoramic view. La Paus, French for the thumb, is a distinctive peak in Mauritius that, despite its modest height of 812 meters, offers views of virtually all of Mauritius from its summit. This island nation in the Indian Ocean is small enough that from the right vantage point you can see from one coast to another, and La Paus provides exactly such a vantage. The peak gets its name from its thumb-like appearance when viewed from certain angles, and climbing it has become a popular activity for both locals and tourists seeking to gain a bird's-eye perspective on the entire island. From the summit, you can see Port Louis, the capital, the surrounding mountains, the coastline, and on clear days, the neighboring island of Réunion. It's a reminder that you don't need extreme altitude to gain profound perspective. Sometimes a moderate peak in the right location can reveal more than a much taller mountain elsewhere. Not all changes to mountain names happen due to conquest or political upheaval. Sometimes they happen through the peculiarly human need to maintain records and rankings. Mount Kosciuszko, Australia's highest peak on the mainland at 2,228 meters, actually swapped names with a nearby peak to remain Australia's highest mountain. The Polish explorer Paweł Edmund Strzelecki climbed what he believed was the highest peak in Australia in 1840 and named it Mount Kosciuszko after the Polish-Lithuanian national hero. However, later surveys revealed that a nearby peak was actually slightly higher. Rather than demote Kosciuszko to second place, authorities decided to simply swap the names. The higher peak became Kosciuszko, and the originally named peak became Mount Townsend. This allowed Australia to maintain the name Kosciuszko for its highest summit, preserving the historical continuity and the honor Strzelecki had intended, even if the name now applies to a different physical mountain than the one he originally climbed. It's a pragmatic solution that prioritizes cultural meaning over geographical precision, showing how our relationship with mountains is as much about the stories and meanings we attach to them as about their physical characteristics. Political naming and renaming of mountains has been particularly pronounced in regions that have experienced significant political changes. Ismail Simoni Peak in Tajikistan, the highest point in the former Soviet Union at 7,495 meters, has had several names reflecting the shifting politics of the region. It was originally called Garmo Peak, then was renamed Stalin Peak in the 1930s during the Soviet era to honor the Soviet dictator. After Stalin's death and the subsequent denunciation of his cult of personality, it was renamed Communism Peak, a less personally focused but still ideologically charged name. Following Tajikistan's independence from the Soviet Union in 1991, the mountain was renamed again, this time taking the name of Ismail Simoni, the founder of the Samanid dynasty who ruled in the 9th and 10th centuries and is considered the father of the Tajik nation. Each name change reflected the dominant political ideology of its time, from regional geography to personality cult to communist ideology to post-Soviet nationalism. The mountain itself remained unchanged through all these renamings, but what it symbolized and how it related to national identity shifted with each new designation. Some mountains have evaded explorers and climbers not necessarily due to extreme difficulty but due to mapping challenges and political restrictions. Gangkhar Puensum, on the border between Bhutan and China, holds the distinction of being the highest unclimbed mountain in the world at 7,570 meters. Part of the reason it remains unclimbed is that Bhutan banned mountaineering on peaks above 6,000 meters in 2003 due to religious and cultural concerns, believing that such mountains are sacred and should remain inviolate. But even before that ban, the mountain had evaded climbers partly because its exact location and the best routes to approach it were unclear. The border between Bhutan and China in this region has never been precisely demarcated, and there's actually some dispute about whether the highest summit lies in Bhutan or China. Early expeditions struggled even to find the mountain, hampered by incomplete maps and the remote, difficult terrain of the region. Several attempts were made in the 1980s and 1990s, but none succeeded in reaching the summit. And now with the climbing ban in place, Gangkhar Puensum seems likely to remain unclimbed for the foreseeable future, the last great unclimbed peak, a mountain that will keep its secrets not because humans lack the technical ability to climb it, but because we've chosen to leave it alone. Mountains can interfere with our modern navigation tools in unexpected ways, a reminder that despite all our technology, we're still subject to the physical properties of the Earth itself. Some mountains disrupt magnetic compasses due to their mineral content, particularly when they contain significant deposits of magnetite or other magnetic minerals. A compass works by aligning itself with Earth's magnetic field, but local concentrations of magnetic minerals can create their own magnetic field strong enough to pull the compass needle away from true north. This can cause navigational errors ranging from minor deviations to complete unreliability of the compass. Mountaineers and hikers in certain regions have long known about magnetic anomalies that make compass navigation treacherous. Iron-rich volcanic rocks are particularly prone to creating these disturbances, as are areas with magnetite deposits. In some locations, the magnetic deviation can be so severe that compasses spin uselessly or point in completely wrong directions. Before GPS became widespread, these magnetic anomalies were serious hazards, particularly in bad weather or whiteout conditions when visual navigation was impossible. Even today, wise mountaineers carry multiple navigation tools and don't rely solely on electronic devices that can fail, understanding that mountains have properties that can confound our instruments in ways we might not anticipate until we're already in trouble. Mountains can also produce phenomena that seem almost magical in their strangeness. Huashan, one of China's 5 great mountains and a sacred Taoist site with incredibly precipitous trails and temples perched on cliff edges, emits faint blue light under certain conditions through a process called triboluminescence. This is light produced when certain crystals are stressed or fractured, essentially the energy of breaking molecular bonds being released as photons. When rocks containing the right minerals, particularly quartz, are subjected to pressure or stress, they can emit this faint glow. On Huashan, the phenomenon has been observed during earthquakes or when rocks fracture, creating an eerie blue luminescence that appears in the darkness. Triboluminescence is the same phenomenon you can observe when you crunch a wintergreen mint in the dark. The breaking of sugar crystals produces brief flashes of light, but seeing it occur in a mountain setting is far more dramatic and mysterious. For ancient peoples who witnessed these lights without understanding their cause, they must have seemed supernatural, perhaps contributing to the mountain's sacred status. Even today, with scientific understanding, there's something uncanny about a mountain that glows in the dark, as if the stone itself were alive with some inner fire. Volcanic mountains, despite the destruction they can cause during eruptions, create some of the most fertile soils on Earth. Mountains like Vesuvius, the volcano that famously destroyed Pompeii and Herculaneum in 79 CE, produce soils rich in minerals that plants need to thrive. When volcanic rock weathers and breaks down, it releases nutrients like potassium, phosphorus, and various trace elements that are essential for plant growth. The soils around Vesuvius and in volcanic regions worldwide tend to be exceptionally productive, which is why people continue to live in the shadow of dangerous volcanoes despite the risks. The agricultural benefits are so significant that they outweigh the threat of eruption in people's calculations, or at least they seem to until the mountain explodes again. This creates a recurring pattern throughout history where volcanic regions are densely populated, get destroyed by eruptions, and then gradually repopulate as people are drawn back by the fertile land. The slopes of Vesuvius today are covered with vineyards and farms, towns, and cities cluster around its base, millions of people living within the potential reach of future eruptions, trusting that they'll have warning enough to evacuate, or simply not thinking about the risk in their daily lives, focused instead on the benefits the volcanic soil provides. Not all human interactions with mountains involve climbing them or living on their fertile slopes. Sometimes we simply destroy them. Strip mining, particularly for coal, removes entire mountaintops in a process that's exactly what it sounds like: the systematic destruction of mountains to access resources beneath. In the Appalachian region of the United States, mountaintop removal mining has literally reshaped the landscape, flattening hundreds of peaks to extract the coal seams within. The process involves using explosives to blast away the rock above the coal, removing up to several hundred vertical meters of mountain, then extracting the coal and dumping the excess rock and soil into adjacent valleys. The scale is almost incomprehensible. Individual mining operations can destroy dozens of square kilometers of mountain landscape, burying streams, eliminating forests, and permanently altering the topography. What was once a forested mountain ridge becomes a flat plateau of compacted rock and soil, the streams that flowed from the mountain buried under millions of tons of mining waste. The coal companies argue that this creates flat land for development and that it's more efficient than underground mining, while environmental groups point to the irreversible destruction of ecosystems, the contamination of water supplies, and the loss of mountains that took millions of years to form. It's a stark example of how human timescales and priorities can clash with geological timescales, how our immediate needs or desires can motivate us to undo in a few years what took epochs to create. Yet despite the changes humans inflict on mountains, some ranges have endured for periods of time that dwarf human history and even dwarf the history of complex life on Earth. Ancient mountain ranges date back billions of years, not the current mountains themselves in most cases, but the geological structures and the roots of mountains that have been worn down and re-elevated repeatedly. These ancient ranges have witnessed nearly the entire history of our planet, standing through the evolution of the atmosphere, the emergence of life, mass extinctions, the movement of continents. Everything that has happened on Earth has happened in the presence of these ancient geological features. The Aravalli Range in India is among the oldest mountain ranges on Earth, with rocks dating back nearly 3 billion years. This range runs through Rajasthan and Haryana in northwestern India, and while its current peaks are not particularly high, worn down by hundreds of millions of years of erosion, the geological structures beneath are ancient beyond easy comprehension. The rocks of the Aravalli tell stories of early Earth, of ancient oceans and volcanic activity, of the formation of some of Earth's earliest continental crust. 3 billion years ago, the Earth was a radically different place. The atmosphere contained little oxygen, Complex life did not exist. The continents were smaller and arranged completely differently. Yet even then, mountains were forming, and some of those ancient formations persist in the Aravalli Range, weathered and transformed but still present, still bearing witness to the deep history of our planet. Even more ancient are the rocks of the Himalayas Range in Western Australia, which date back over 3 billion years. This range contains some of the oldest rocks on Earth's surface, banded iron formations that tell the story of Earth's early atmosphere and oceans. These distinctive rocks, with their alternating layers of iron-rich and iron-poor minerals, formed in ancient seas when dissolved iron reacted with oxygen produced by early photosynthetic bacteria. The oxygen would cause the iron to precipitate out of the water and settle to the seafloor, creating these banded formations. The Himalayas Range thus preserves direct evidence of one of the most important events in Earth's history, the Great Oxidation Event, when life began producing oxygen and fundamentally changing the planet's chemistry. Looking at these rocks, you're seeing evidence of processes that occurred over 3 billion years ago, when Earth was less than a third of its current age, when the day was shorter because Earth rotated faster, when the moon appeared larger in the sky because it was closer to Earth. These mountains are time capsules preserving conditions and processes from Earth's deep past.